In the beginning of this section, we talked about the idea of using rectangles to approximate the area of a bounded region. And we can see that the more rectangles we're using, the better the approximation will be. For example, here we wanna approximate the area of the region bounded by this red line and between x equals 2 and x equals 5. So the exact area of this region is 19.5, and if we use 8 rectangles, the approximation is 21.2. Now if we increase the number of rectangles to 20, so the result will be 20.17, which is close to the actual result, right? And the more rectangles I'm using, you can see the result will be better, and better. When I use like 100 rectangles, the difference between the approximation and the exact area will just be less than 0.2. So this shows us when we increase the number of rectangles, we can improve the approximation. So during this process, what happened to the rectangle is the width of the rectangles are getting smaller, right? In other words, each rectangle, it becomes thinner and thinner, right? Okay, so in this video, we're going to talk about how to use this method to find the exact area. Now we are not talking about the approximation. We want to find exactly what the area of the bounded region is. So we're gonna do this by using the limit definition. Okay, so we know to get a better approximation for the area on the curve, we should increase the number of rectangles. If we could draw an infinite number of rectangles and add up their areas, we could find the exact area. However, we know this is impossible, right? It's impossible to draw infinite number of rectangles. So therefore, we want to develop a formula that gives the area under the curve. So we want to the formula we develop. So we want to start developing a formula of using n rectangles. Okay, so here n indicates the number of rectangles. So after we found this formula, so the formula will contain the variable m, and then if we take the limit of that formula as n approaches infinity, so that will give us the exact area of the bounded region. Okay, so let me use this example to illustrate this idea. Here we have this function f(x) equals x squared. So the graph looks like this. And we want to find the area of the region bounded by this curve and x-axis, and bounded by x equals 0 and x equals 1. Okay, so the area we're looking for is okay, is this. Okay, all right, so we said first we want to develop a formula of n rectangles. So here we consider to use n rectangles. Now the first thing we need to do is to figure out how to determine the width and the height of each rectangle. Now we said to determine the width, it's easy. Because why? Because each rectangle they have the same width, right? Now, since there are n rectangles, and the distance from these 2 points is 1. If we have n rectangles, then the width of each rectangle gonna be equal to this distance divided by n. So it's 1 over n. This is the first rectangle, the base of the first rectangle, and the base of second rectangle, the base of the third rectangle, all the way to the last, the nth rectangle. Okay. Okay, and then when we decided the height of each rectangle, we wanna first determine which method do we use. We can use either the left endpoints method or the right endpoints method. Okay. Once we decide which method we want to use, we're gonna use that method to every rectangle. So here, let's say we are using. I want to use the right endpoints method to determine the height. So the height of the first rectangle, I'm gonna use the function value at this point to determine. Now the question is, now I know the function is fx equals x squared. Now how do I know what this point is? What is the coordinate of this point? Now remember, since we know the width is 1 over n, that means for each consecutive point, their distance is 1 over n is equal to this number 1 over n. So since this first point is 0, therefore the next point gonna be 1 over n. So this point gonna be 1 over n. Therefore the height, we can find that. So the height of first rectangle, we can find it. It's the function value. It's the function value at this point at 1 over n, which is 1 over n squared. Okay. For the second rectangle, I use this point to determine its height. Now this point and 1 over n, since their difference is 1 over n, so this point, the coordinate of this point is 1 over n added by 1 over n, so it's 2 over n. Therefore the height of the second rectangle gonna be f of 2 over n. So it is 4 over n squared. From these two terms, we can see that there is a pattern. The pattern is the height of the ith rectangle can be represented by the function value f of I over n, right? The first rectangle, the height is f of 1 over n. The second rectangle, the height is 2 over n. So the ith rectangle, the height is f of I over n, which is I square over n square. And for the last rectangle, for the nth rectangle, we use the endpoint 1 to determine the height. So that is f of 1, which equals 1. Okay. After we have found the width and the height of each rectangle, the area of this bounded region can be approximated by the sum of the area of these rectangles. So the area of the sum of the rectangles we can write into this form. It is the height of the ith rectangle multiplied by the width. Okay, so this product gives us the area of the ith rectangle. And since we have n of this, we have n rectangles, so we add up them together by using the sigma notation we started before. So this area we can write as the sigma of I square over n square times the width, 1 over n. So remember, this is only the approximation of the bounded area, of the bounded region, of the area of the bounded region by using n rectangles. Okay, so the next thing is we wanna figure out what is this result is by using so we wanna write this in terms of n, in terms of n. So if we look at this summation, we can see that here n is a constant, because every term has this n, because this is like this is like 1 square over n square times 1 over n plus because the I is the index, right? So the variable is only I. So the next term is when I equals 2, that is 2 square, 4 over n squared times 1 over n. And when I equals 3, that is 3 square over n squared times 1 over n. So each term has a common factor n 1 over n squared and 1 over n. Therefore, we can fact out that. So we can fact out 1 over n to the third. And what we are left in the summation is the I square. Okay. Then using the formula we learned from sigma notation, the sigma of I square equals this, n times n plus 1 times 2n plus 1 over 6. So this sigma notation equals n times n plus 1 times 2n plus 1 over 6. So the total is n times 2n plus 1 over 6n to the third. And we can cancel out n. So get n plus 1 over 2n plus 1 over 6n squared. So this is the formula we want to divide. So okay, so what this formula tells us is if we use n rectangles to approximate this this area, that result gonna be equal to this. Okay, we can try some numbers like here. Okay. We can so this is fx equals x squared. Okay, let's look at this one. So this is the region bounded by the function fx equals x squared and x equals 0 and x equals 1. So the exact area of this region is 1 over 3. Okay, it's 1/3. So if we use 10 rectangles to approximate this area, then when n equals 10, the approximation will be 10 plus 1 times 20 plus 1 over 6 times 10 squared times 100. That is 11 times 21 over 600. So it's 0.385. And if I use 50 rectangles, then the approximation is 50 plus 1 times 2 times 50, 100 plus 1 over 6 times 50 squared. So it's 2500. divided by 6 and divided by 2500. So it's 0.3434. We can say when I increase the number of rectangles, the approximation improves, right? Now remember, our goal is to find the exact area. So now we're gonna do is we're gonna take the limit of this result. Okay, we let n approach infinity. Okay, and that will give us the result of that will be the exact area of this bounded region. So to find the exact area, we wanna evaluate what is this limit. Okay, so to evaluate this limit, we can first multiply the numerator out. So we can get 2n squared and plus m plus 2m plus 1 over 6n squared. And this equals the limit of 2n squared plus 3m plus 1 over 6n squared. Okay, now we can say as n approaches infinity, the numerator and the denominator both approach infinity, right? So this limit has the form infinity over infinity. And we said when the limit has the form infinity over infinity, the result depends on the coefficient of the leading term. Now the leading term of the numerator is 2n squared, and the leading term of the denominator is 6n squared. Since the degree of these two leading terms are the same, so the limit equals the ratio of the coefficients, which is 2 over 6, which is 1/3. So the exact area of this bounded region, just as what we saw here, is 1/3. Okay, so that is the exact area. Okay, let's review this process. So to find the exact area, we first decide to use n rectangles, and after we figure out how to write the width and the height of each rectangle, we construct this summation. Okay, and then using the summation formula we learned early to figure out how to write this summation in terms of m. So we can get a function. So this is like a function of n, and then and this function represents the area when we use n rectangles to approximate. And to find the exact area, we evaluate the limit. We let n approaches infinity, and that will give us the exact area of the bounded region. Okay.